Hi guys, in this video we are going to discuss few more questions on transformers. Okay guys, let's see this question. If a sinusoidal voltage source is connected to power transformer, its no load current would be. What about the no load current? You know already the vector diagram. How the vector diagram will be for a transformer under no load condition. For example, here is our IW, working component of current, and here is our I mu, magnetizing component of current. Always the magnetizing component of current more than the working component of current, and sum of IW and I mu taken as the no load current, and the angle between these two is a phi naught, no load power factor angle. So the no load current is lags behind the voltage by around 75 to 80 degrees, or simply less than 90 degrees, or it may be nearly equals to 90 degrees, whatever it may be. Yes or no guys? So which is correct answer? Is this is sinusoidal or non-sinusoidal? I already told you generally voltage may be sinusoidal, but due to third harmonics the current is non-linear, non-sinusoidal. So which is the suitable answer, sir? Rich in third harmonic and fundamental will be lags the voltage by less than 90 degrees. One option is there less than 90 degrees and another option is there equal to 90 degrees. So which is suitable answer, sir? Can you tell me? The less than 90 degrees will be the suitable answer. So like a questions also they may ask you, sir. This is also important. Next question. Let's see the match the following. List 1, list 2 is there. Which of the following is a power transformer? Generally the power transformer where we are using in generation and transmission, which is a high voltage transformer. Which is suitable for power transformer? The only one we have this one, which is greater than 33 kV. Auto transformer, we'll see later. Welding transformer is a step down transformer, and the welding voltage just in terms of 100 volts, 120 volts, etc. So the step down transformer will be the welding transformer. What about isolation transformer? You know, when the primary and secondary both are same, that is called isolation transformer. So the remaining is the auto transformer. Yes, sir, how you can take that as a auto transformer? Because generally the auto transformers are preferred where K value is nearly equals to 1. It may be greater than 0.5, 0.6, 0.7, whatever it may be, nearly equals to 1. Sir, which of the following have K nearly equal to 1? And remember that in auto transformer K is equals to LV by HV. For this transformer, LV is a 220, HV is a 240, which is nearly 11 by 12, almost 0.9 change, nearly equal to 1. That's why that is suitable for auto transformer. Now tell me, which is correct answer? A 4, B 2, C 3, D 1. Option A will be the correct answer. Next one, again match the following. Silica gel, where we can use silica gel. The silica gel will be there in the breather to absorb the moisture and the dust particles from the atmosphere air. And porcelain bushings are used. And mercury used in Buckau's relay is a mercury floats will be there. Mercury used in Buckau's relay. Fins used for a transformer tank for heat dissipation. Like a radiators, we can use fins also for heat dissipation. So this is simply A4, B1 will be the correct answer. Right, next question. In iron core of a transformer is replaced by air core, the hysteresis loss. I already told you for air core transformer the BH curve is linear. When the BH curve is linear, what about hysteresis losses? The hysteresis losses equals to 0. So already you know generally the BH curve for dia, para, ferro. Generally if this is a 1 where mu r is equals to 1, generally we consider for air mu r is equal to 1, which is a linear curve. The area BH curve is 0. If it is a dia, the BH curve is like this. If it is a para, the BH curve is like this. If it is a ferro, for ferromagnetic material, BH curve will be like this. So for air, the curve is linear. When it is a linear, the hysteresis losses becomes 0. Hysteresis losses becomes 0. Okay guys, you know already. Next question. If the voltage applied to transformer primary is increased by keeping the V by F ratio fixed, then the magnetizing current and core loss will respectively. What happens here? Here B maximum is constant. B maximum is constant. Of course, we are increasing the voltage, but we are keeping the B maximum constant. Nothing but if the voltage doubled, the frequency also doubled. When both cancel, the B maximum is constant. When the B maximum constant, there will be no change in I mu. There will be no change in IW. There will be no change in IW. Remains same. Remains same. Both will be remains same. Okay. Next question. Again, this is also match the following. See, magnetic flux. Okay, electrical and magnetical analysis. What we called analogy. Same, which are similar. In magnetic circuits, magnetic flux similar to the current. Magnetomotive force, electromotive force. Reluctance, which is similar to resistance, and permeability and the conductivity is similar. So A2B4, A2B4, this will be the correct answer. Next question, sir. Tappings are normally provided to the high voltage winding of transformer only because. Why we have to provide tappings only on high voltage side? Why only on high voltage side? It has large number of turns which allow smoother variation, of course. It has to handle low currents. Yeah, of course, on that side low currents will be there. It is easily accessible physically. It has larger number of turns, has to handle low currents and easy accessible. Okay, all they combined in the last option. That's why we are using only on HV side. 17th. Next question. Let's see this question. Do you have an answer for this question? A magnetic circuit has 150 turns coil. 150 turns coil. Cross-sectional area they given 5 into 10 to the power of minus 4 meters square. The length of the circuit they given 25 into 10 to the power of minus 2 meters. Everything given in the meters. What are the values of magnetic field intensity? Do you know magnetic field intensity? Ni by L. N is a 150. I, is there any I? And relative permeability they are asking. Magnetic field intensity and relative permeability when the current given is 2 amperes. Current given is 2 amperes and the length given is 25 into 10 to the power of minus 2. 25 ones, 25 six. So the answer is 1200. 1200 ampere tons per meter is the magnetic field intensity or magnetic field strength. What they are asking now? They are asking relative permeability also. Relative permeability also. Relative permeability and they given flux. What they given flux is equals to 0.3 milliwebers. 0.3 milliwebers. How we can calculate relative permeability? Very simple, sir. We have we have to calculate flux density. Flux density is equals to flux per area, where the flux is a 0.3 milliwebers, and area. What is the area? 5 into 10 to the power of minus 4. Nothing but plus 4 is a plus 4 nothing but 30 by 5. 30 by 5 nothing but simply 6 Tesla. Flux density is a 6 Tesla. Sir, if you know the flux density, how we can calculate mu r? Very simple. B is equals to, or simply mu is equals to B by H. Do you know? Mu is equals to B by H. Mu is nothing but mu naught into mu r is equals to B by H. That's it. Mu naught 4 pi into 10 to the power of minus 7 into mu r is equals to B is the 6, H is a 1200. H is a 1200. 6 ones are 6 twos are 1 by 200. Where mu r is equals to what happens, sir? Can you tell me? This minus 7 will come as a plus 7. Plus 7 by 200 into 4 into pi. 200 into 4 into pi. What will be the correct answer? Yes? Is there any points are there? What they asked first of all, magnetic field intensity is at 1200 and relative permeability may be 400 around. Let's see, we'll discuss. 2 zeros cancel, remaining 5 zeros will be there. 2 fours are 8 into 3.14. 8 into 3.14. Yes, 8 into 3.14. Is it okay? Now can you tell me what is the answer? 8 into 3.14, 10 to the power of 5 divided by 8 into 3.14. Just I will calculate here. 1 divided by 8 into pi is a 0.04. 0.04. Can you calculate the answer? How much? Divided by 8 into 3.14, around 398. Something will be there around 398. This is our answer. Is it okay? This is simply what about magnetism basic question. In the question from magnetism basics. The question from magnetism basics. Here minus 1 be there, plus 1, 3 by 5. This is 0.6. This is 0.6. Here also 0.6. 0.6. When you take it is as a 0.6, then we will get that. 0.6 by 1200. Now if you calculate mu r, you will get 398, around 398. Okay, sir? Here small mistake. This is not 6, sir. This is 0.6. So you have to remember that mu is equal to B by H. Is a very basic formula. Based on that they asked this question. Let's go for next question. The ideal core should exhibit very high permeability in case of transformer and inductor core due to magnetic saturation caused by DC imbalance condition. That can be minimized by. The DC imbalancing conditions can be minimized by. Actually here, ideal core should exhibit very high permeability generally. When that is a very high permeability, we should go through the high reluctance or low reluctance. Yeah, low permeability and high permeability combination they given in the option. When it is high permeability, high reluctance and low reluctance paths are there, it can imbalance. The DC imbalancing condition can be minimized by the low permeability and high permeability combination. Both will be there. In the transformer core, we should have both the high permeability combination as well as the low permeability. When we are using both combination, at low reluctance path, it can choose high permeability. At high reluctance path, it can choose low permeability path. That's why we can make it minimized by using combination of low and high permeabilities. This is also basic question. Next and last one. What are the important characteristics that must be satisfied for the material used to build the core of transformer? Used to build the core of transformer, which are the satisfying parameters? Yes, can you tell me? High permeability ultimately It should be have high permeability, low hysteresis, ultimately low hysteresis, and high eddy currents, and low Curie temperature is a low coercive force, ultimately low coercive force of course, and low Curie temperature. The Curie temperature should be high. It should not low. So the answer will be high permeability, low hysteresis loss and eddy current loss. Low hysteresis loss and eddy current loss. Low hysteresis and high eddy current loss is wrong. Low hysteresis and eddy current loss. High hysteresis is wrong. Low Curie temperature is wrong. So which is suitable? Option B will be the suitable for this. Is it okay, guys? Is it clear, every one of you? This is what about the transformer basical, about the construction, up to the construction part what we discussed up to now. In the next video, we'll discuss its advanced level, like a EMF equation, like a losses and efficiency concept we'll discuss in the next videos. Thank you, guys.